Hi, Physics 2. Mr. Janowski again. This is part 7 of the Chapter 35 slides. We're going to do something here in this part. We're going to do math that I'm not actually going to test you on. It's beyond what we're doing in this class. But I just want to show it to you because if you stick with the physics and you stick with STEM, you will have to be able to do this kind of math in the future in college. So consider this, the math in here, enrichment. The basic formula and how you use it, that you will have to know. But how you actually derive it, that's more of a college level type question. So I'll go over it and we'll see. So let's get started. So think back to last chapter. I think it was last chapter. It might have actually been the chapter before. But what is the formula for the capacitance of parallel plates? Remember when we did capacitors? And that formula is capacitance equals this constant, epsilon naught, that's the permittivity of free space, times the area of one of the plates divided by the distance between them. So, think two plates. Each plate has an area. They're separated by a distance, and it's multiplied by this constant. So that's how you figure out the capacitance. So bigger plates get you bigger capacitance. Smaller separation, if you bring the plates together, that also gets you bigger capacitance. So also remember from last chapter, what's the formula that relates capacitance, voltage, and charge? QVC, Q equals VC. Think of this goofy home shopping network type channel. Has your little mnemonics. Remember this. Charge equals the voltage across the capacitor times the capacitance. So we're going to figure out the formula for finding the equivalent resistance of capacitors in series. So in this case, we have 3 capacitors in series. If the switch is open, no charge is going to flow. So if we close the switch, it's a little weird what happens with capacitors. So we're actually going to look at the electrons and not the current in this case. What's going to happen is if you close the switch, now charge can flow, and electrons are going to leave this plate and head towards the positive terminal here. And electrons are also going to, let me go this way. Once charge can flow, the electrons that were on this plate are going to leave here. That's going to leave this plate with a bit of a positive charge. It's now lacking electrons, so it's positively charged. And that's going to draw electrons from this plate over to here. So now this plate is positively charged. And that's going to draw electrons from this plate over to here. So now this one is positively charged. And that's going to draw electrons from this terminal of the battery all the way around to here. So this is the way the electrons are going, counterclockwise or anti-clockwise. We would say the current is actually going the other way. So after a while, the voltage across all of the capacitors, after a while, you'll have a charge of Q on the positive plates and a charge of negative Q on all the negative plates in this case. And once the capacitors are fully charged, the total voltage across each of the capacitors must equal the voltage being provided by the battery. So what's the idea that tells us this must be the case? KVL, Kirchhoff's voltage law. So if you make a loop, start lower left and go clockwise around, this would be a gain, and then each one of these would be a drop. And it turns out that each of these drops, the sum of all of these drops must equal the gain. So here's what we can get from KVL, and then we sub in this idea, Q equals VC, so V equals Q over C. And then you just divide everything by Q, and you're left with this. So we end up with this formula for the equivalent capacitance of 3 capacitors in series. So what is this telling us? This is telling us that capacitors in series add inversely. When they're in series, they add the weird way. So capacitors in series add like resistors in parallel. So this is how you derive that relationship. You don't necessarily have to know how to derive it. You do need to know what the relationship is, though. By a similar token, if you have 3 capacitors in parallel like this, you can kind of think of these guys as just making one much bigger area. So if that were true, think of this If the area is getting bigger, what's happening in the capacitance? The capacitance is going up. So what does this tell you? Capacitors in parallel add normally, meaning they add like resistors in series. So this one especially was not a very rigorous derivation of this idea, but we'll just go with it to save time. So, who is this guy? Math fans, you should know this person's name. This is Leonhard Euler. I used to think it was Euler, but it's not. It's definitely Euler. Very famous, extremely prolific Swiss mathematician. This guy wrote like encyclopedias worth of mathematical papers. Had a crazy kind of photographic memory. You could ask him, like, what was the fifth line on page 72 of Virgil's Aeneid in Latin, and he would tell you. He knew all this stuff by memory. Crazy, very bizarre person. I think Virgil wrote the Aeneid. I'm not sure. Anyhow, yeah. Crazy brain in this guy. So yeah, Leonhard Euler, one of the most famous mathematicians of all time. So what is Euler's number? Euler's number is E. It is the base of the natural logarithm. This E, since we're talking about electricity, this is not lowercase e for the fundamental charge, the charge of a proton or an electron. This is E, the base of the natural logarithm. It's a transcendental number. So ask your math teachers what that means. It's got a funny definition. But yeah, E is one of these long irrational numbers and transcendental numbers. 2.718, et cetera, et cetera. Very important number throughout math, and especially if you're doing things with exponentials. And hey, exponential growth, that's been in the news lately. You may be aware. So let's consider this circuit. We've got a battery hooked up. We've got a couple switches, and we've got a resistor and a capacitor. So in this first part that we're going to do, just ignore this switch completely. Switch 2 isn't going to do anything for us. It will be involved in something we're going to do later, but not in this part of the slides. So all this is set up, and the capacitor is initially uncharged. We just took it out of the box, plugged it in. There wasn't any charge in the capacitor. So if we close the switch, what's going to happen is, electrons are going to flow counterclockwise to the positive terminal of the battery. But we're going to say current flows clockwise around the battery like this. So one thing that's always seemed kind of weird to me, if you think of what's happening at the capacitor, so we're going to follow the current. We're going to say positive charge. Actually, for this one, let's follow the electrons. It'll make more sense. So what actually happens is electrons leave this plate and come to here, the positive terminal. And the fact that we're losing electrons at this top plate here is leaving this one with a positive charge. Well, that's going to draw electrons from the negative terminal of the battery around to here. So it looks like negative charge is flowing counterclockwise, and it looks like positive charge is flowing clockwise. But the kind of weird thing is that no charge actually flows through the gap in the capacitor. It could be different things, but let's say it's just air. So the electrons flow through the wire. Well, they flow this way. But nothing actually flows through that gap. It just kind of seems like they do. So whatever, that's weird. So anyhow, after we close the switch, charge is going to start to build up on the plates of the capacitor. As soon as charge can flow, you're going to start to end up with a positive charge up here and a negative charge up here. And the charge won't be constant. It will be a function of time. It's going to vary, with time as we, the longer we leave the switch open, the more charge is going to build up. So what do? You do your KVL ideas. You draw a loop, and then you follow this loop around, and you write out what the voltages are. So starting lower left, going clockwise, first thing we get to is this battery, V naught. So we're going negative to positive, so that'll be a gain, so plus V naught. Nothing happens at the switch. A closed switch is just a wire, basically. Then we get to this resistor here. So when we get to the resistor, our loop is going through the resistor with the current, so that's a drop. And then we get to this capacitor, and we're going through this capacitor from positive to negative. Remember, this plate is going to be positively charged, this one's negative. So the capacitor also ends up being a drop. So then we sub in our ideas, Ohm's law and QVC, and we get this equation. And then we remember, current is actually the rate of change of charge over time. So in calculus speak, you would say current I is dq dt. So this I just became this. Then I did some algebra and rearranged it. So you get this guy. dq dt is equal to v naught over r minus 1 over rc times q. So what we've got here is what's called a differential equation. In this equation, q is not a constant. Q is actually a function of time. I could have written it this way, q of t, but I didn't. I just wrote it as q. And in this equation we've got here, you have q, which is a function, and you have the derivative of the function. So yeah, that makes this a first order differential equation. So what we've got to do is find some function q of t that satisfies this equation, such that that function and its derivative meet this equation, make this equation work. So I always get a big kick out of this. One way you solve differential equations is you guess the answer. There's not really other ways to do it. You just have to kind of guess what the answer is. You make a clever guess, and then you just keep refining your guess until you end up with the right answer. Kind of weird. But that's how it works. So we're going to guess that q of t has this form. Q equals some constant k plus some constant a times e, Euler's number, raised to the b, some constant, times t time power. So I don't want to go into why this is the right kind of guess to make. There's different rules for guessing what your equation will be when you're solving, what your function will be when you're trying to solve a differential equation. But yeah, you make a guess. So this is our guess, and it's got 3 unknown constants, k, a, and b, and we've got to figure them out. So first thing we do is we take the derivative of this. So when you take the derivative of that, think back to what Babias is learning you in calculus. The derivative of this equation is going to be this. The derivative of a constant is just 0. If you take the derivative of, we've got a constant times e to the bt, the derivative with respect to t, the b comes down, so you get this. All right, I've just decided I'm going to kind of race through these because I don't want this video to get too long. So yeah, you've got this is our guess for the function. This is what its derivative will be. You plug them back into this idea. You get this, you do some stuff, you do some more stuff, you group, you do algebra, you figure out more stuff, and then eventually you can figure out what k is equal to. Once you know what k is equal to, and we know that, where did that leave us? Okay, we figured out what k is equal to. You've got this, you can now figure out what b is equal to. And then you have to go back and figure out what a is equal to. So you do that using what is called a boundary condition. You know that at time t equals 0, there is no charge in the capacitor. The instant you close this switch, charge hasn't had time to move yet, so there's no charge in the capacitor. So you do some more stuff. You can pause the video, or you can go back to the actual slides that are on Google Classroom if you want to follow this all the way through. But you figure out what A is. So now you have the whole thing, and you now have a formula for the charge Q on the capacitor over time. We, however, are not really interested so much in the formula for the charge on the capacitor. We're going to care more about the voltage. So you use the Q equals the QVC idea, Q equals VC, and you solve this and you get this equation. So this is your equation that relates, your equation for the voltage across a capacitor has a function of time when you've got a charging capacitor. So V sub C, the voltage across the capacitor, is equal to V naught, the voltage of the battery, times this term, 1 minus e to the minus t over RC. So now we're going to look at this a couple of ways. We're going to look at it physically, mathematically, and then graphically. So physically, what's going on? We had this, there was no current. So if there's no current, think of Ohm's law. That means there's no voltage across this resistor. And if there's no charge in the capacitor, think QVC, that means there's no voltage across the capacitor. So then you close the switch, and current starts to flow. So once you've got a current going through the resistor, you now have a voltage through the resistor. And now you're starting to have charge build up here. So you're going to start to have a voltage across the capacitor. But interestingly, the instant you close the switch, when there is no charge on the capacitor, there's no voltage across the capacitor. So the capacitor just lets the voltage go all the way through. Basically, all the voltage that's being held by this battery is going across this, and there's no voltage across this at time t equals 0. Then as soon as charge starts to move, that changes. But at that one instant, there's no voltage across this, so your capacitor with no charge in it is just a short. It's just letting the current go right through as if it were only a wire. But then as time progresses, you've got charge moving. You've got positive charge coming around here, getting to this plate and stopping, and positive charge leaving here and going here. So as time starts to flow, as time flows, you get charge build up on the plates of the capacitor. You start to get a voltage across the capacitor. Once you have a bigger voltage across the capacitor, you're having less voltage through the resistor, across the resistor, I should say. Over time, this is going to stop letting current flow. The instant you close the switch, it just lets current go right through. And then as soon as charge starts to build up, it starts to prevent current from flowing. So the upside of that is a fully charged capacitor after a very long time is just like an open. So you've got a battery, everything's hooked up, you've got a whole complete circuit here. But once all of the voltage of the battery is across the capacitor, none of it is across the resistor, and no more current flows. So if we're looking at this formula, now we're doing the mathematical interpretation. Think, what are the units of RC going to be? So you may know that the units of resistance are ohms, and the units of capacitance are farads. So you could say ohm farads. That's certainly true. But there's another thing to realize. When you take e to this power is not allowed to have any units because of math. Basically, it's not allowed to have any units. So if t is in time, and that's the numerator, your denominator must also be in units of time. So it turns out the units of RC are actually seconds. And here's another way to derive that. So RC, ohms, farads. Well, an ohm is a volt over an amp. A farad is a coulomb over a volt. An amp is actually a coulomb per second. So do some algebra. The V's will cancel, the C's will cancel, and then you have 1 over S, which is just S, seconds. So RC has units of seconds. An ohm farad is the same thing, has a second. So this is called dimensional analysis. Very useful skill to have in science. So that value RC, that's an important value. Sometimes you write it all the way out as RC. Other times you abbreviate it and you call it tau, the time constant. So what time constant is if the time constant is large, it's going to take a long time for the capacitor to charge. If the time constant is small, the capacitor is going to charge relatively quickly. So tau equals RC, and will again be in units of seconds. So one thing we do a lot in science is when you get a formula like this, you try to figure out, what's the behavior of this function? So what is this function going to do when t equals 0? And what will this function do when t equals infinity? So if t equals 0, you plug a 0 in up here. So 1 minus e to the minus 0 over RC, this is just going to be e to the 0. E to the 0 is 1. Anything to the 0 is 1, with the exception of 0. But any other number raised to the power of 0 is 1. So this whole term in parentheses becomes 1 minus 1, which is 0. So V naught times 0 is 0. So at t equals 0, the voltage across the capacitor is 0. So we actually knew that. I've said that a couple times throughout these slides. So what's going to happen when t equals infinity? So if you plug in the number infinity here, infinity is not a number. If you plug in infinity here, as this number starts getting bigger and bigger, what's going to happen with this function? Well, 1 minus e, let's just look at this part. E to the minus infinity over RC. yeah, if this number is infinity and this number is finite, yeah, the finite part doesn't even matter. This just ends up being e to the minus infinity. E to the minus infinity is the same thing as 1 over e to the infinity. So that's just going to tend, towards 0. So you end up with v naught times 1 minus 0, which is just v naught. So what that's telling us is after a very long time, after infinite time, the voltage across the capacitor will equal the voltage across the battery. So here we can look at this as a graph. So this is what's called bounded growth. It's related to exponentials, but it's not actually an exponential. Exponentials tend towards infinity. This tends towards a number. But the graphical interpretation. On the x-axis we have time, and we have time in units of taus. So just kind of a generalized thing. Whatever your value for tau is, that's what you make your vertical dividers. And on the y-axis, we have the voltage across the capacitor. So as soon as you close the switch in the charging capacitor, voltage is going to start to build up across the capacitor. After one time constant, it's about 63% of the way there. After 2, it's 86.5% of the way there, and so forth and so forth. So it just keeps getting closer and closer to the value of V sub c. Now it approaches it asymptotically. It never actually gets there, but it gets really close really quick. So after only 5 time constants, you're 99.3% of the way there. And if you just wait any more time constants than that, you're getting so close to the value of V sub c. I'm sorry, your value of V sub c is getting so close to V naught that you just say, yeah, it's fully charged. It's all the way there, because it's going to vary so little after a while. So this graph is the voltage across the resistor as a function of time. So remember, the instant we closed the switch, the capacitor was acting like a short. So it was just letting current go through, which means we had basically the full current going through the resistor. So all of the voltage of the battery was across the resistor. So at t equals 0, the voltage across the resistor is 100%. But as time goes on and you start getting more and more voltage across the capacitor, you're getting less across the resistor. So it goes this way. So this is exponential decay. So if you did the formula for the voltage across the resistor, you would get this. V naught is equal to e to the minus t over RC. And that's it. So hopefully that was helpful.